Hello, in this video we'll be talking about, or we're doing another example. Now we are plugging in the DQN algorithm and let it work on Cartpole. So yeah, let's get curious. I will turn off my video again because not to distract you. And as always, you will find the necessary material for download on the web page. So first, activating this one. I also provide this in a Jupyter notebook environment here. So sorry for this one. It's Q Learning. No, it's DQN Cartpole. Plug this in and start this. So you will see the window. So what you find here is you find some folders. The only important one is this one. So if we're gonna go in, you see as in the beginning, you see some general information about DQN and itself and some mathematical and some remarks on this. But the really important one is beginning in here. So this implementation uses stable baselines. This is not OpenAI baselines itself. It's a fork from OpenAI baselines and making their APIs more like equal to each other. So stable baselines is just a wrapper over the original baselines code. You can just run it. And at some point it also should work. You get some errors because of TensorFlow, but this is not big of an issue. In this environment, we will use the Cartpole v0 environment, which is basically a continuous environment with a discrete state space. We will run for 2,000 episodes and 50,000 iterations. So we will define a logging directory. We predefine the logging directories on the folder. Let me only just give a hint if these are empty or not. So if you make them empty previous to your runnings, then it will make it more convenient to you to see the actual results. So make sure that they are empty, and so we can define the logging directories. We define a vectorized environment. This is actually something that's that's only for stable baselines. And here it comes. We will now initialize our DQN agent. So you can use a lot of different parameters that you can choose upon. Many of them there's default parameterizations on this, but the most important are, for instance, the learning rate, which is a crucial one, the buffer size, which is basically the experience replay memory size. Then we have our exploration specific things. This is not only the exploration factor, but also the annealing schedule for it. Training frequency. This means that how many iterations should the agent wait between the different experience samples to actually train. So using one just means that with any new example we take from the environment, we will train a mini batch on our training, and we will use a batch size of 32 on it. We will use double Q learning. We will make a warm start, which means that we wait until we fill our buffer before we start. Every 500 time steps, we will actually update our target network, which is just saying that we will copy the weights. We will not do any prioritized replay. We want to have some verbosity, and we will log everything to TensorBoard. So we can just run our agent. It's just initialized. In here, we define a callback function to just get a little bit of a feedback during the course of the training. Here we define a function that evaluates our DQN agent. So we want to evaluate and get the reward of our agent, not for the epsilon greedy policy during training, but for a greedy policy that we run in parallel to our training course. Here we want to evaluate our agent before we actually train anything. So in Cartpole, in this one, we ran 69 episodes and got a mean reward of 29. Cartpole is considered to be solved with a reward of 200. So actually this means that on average, our agent achieved to balance the pole for 29 time steps. So if we want to train the agent, we first do some, we take the time and then we train the agent. This takes a minute. I will maybe cut it out and start TensorFlow in between. No Mensch. So looks like we're done. So we trained for 50,000 time steps, and what you see is that at the end we get a last mean reward per time step of close to 200, which basically means that we solved Cartpole. In the meantime, I also started TensorFlow. Here in TensorFlow, you can look over the episode reward over the course of training, and you see also a lot of different information for the TD error over time and also for the loss. Yeah, so this actually worked out. So we trained an initial agent, and what we also want to do is we want to plot For example, the reward of the policy that our deterministic policy or greedy policy achieves, and this would look like this. So what you see is, you see that actually there is points of time and evaluation iterations that actually solved Cartpole, but you also see that there's instability. So actually at some point, some smaller changes to the Q function actually leads to different actions, and these actions then lead to the fact that the pole falls over. But in fact, this is a good sign. So actually at some points we would restore this policy or this value function. We saved every one of these models, and actually we can then use this model that we obtained from this value function actually to perform, to actually do control in practice. So yeah, if you want to evaluate the best agent after training, we can also have a look at it. So this is the restored best agent from our policy, and what you see is that for any of those cases, the pole is balanced for 200 time steps, and that is also when the window resets and actually the pole starts over again. Yes. Sorry. Now I see you don't see the window because it's on my other screen here. So now maybe we should do it again. So actually, I will close it again. Yeah. So and what you see now is, although it is always creepy, what you see now is that the pole balances, and the agent manages to balance the pole for almost always 200 time steps. And this is also then the point when the environment actually resets, starts over again in the middle, and the pole balancing task goes on again. Yeah, we can also close the environment and stop it, and maybe go on. Yeah, so as we already heard in the linear value function approximation issues, when we go to nonlinear function approximation, how to properly tune our hyperparameters becomes much more critical. So in this example, I want to show you 3 different things. Sorry, this was not meant to be. So the first of all, we want to actually evaluate the architecture of the neural network. So we could either go through the depth of the neural network or through the height of the neural network. What I want to do is I want to change the architecture, having only one hidden layer with 2 neurons until two hidden layers with 246 neurons each. We want to also evaluate the influence of the learning rate, and we want to learn the influence on the size of the replay buffer. So we will start with the neural network architecture first, then we will look into the learning rates, and then we will look into the replay buffers. So this is to initialize our hyperparameter search, and now let's run the test for the sorry, this is not working. I will check this in the, I think this is this one. I will change this. So yeah, we start training, and the model will be trained, and we are back as soon as the model are trained, and then we can have a look at the results in the TensorBoard. So, okay, we're back. All of the runs did get through. Took about half an hour. So here are the results. So this was the original 2 times 260 56 layers. What you see is if you only take one hidden layer with 2 neurons, that you actually don't learn anything. So the capacity of your neural network is way too small to actually get anything running. The same actually holds also for if you use 2 hidden layers with 2 neurons each. So actually the capacity of your neural networks is just too small to extract and take the information and approximate the value function properly. So if you use one layer with 64 hidden units, this is actually what you get. So you get actually a pretty decent result already. So, and if you increase to 128 or 246, 56, you actually get pretty decent results, and you can actually say that the value function can sufficiently actually be approximated using only one hidden layer with 64 units. So if you increase the number of hidden layers, actually, what you see is that you will not even be better. In this case, you do not see it so clearly. Maybe we make the direct comparison to the 128. What you actually see is that with a growing number of hidden layers, it actually gets harder to actually approximate the value function. So what you see here is currently that the blue line is clearly above the orange line, although there's high variance in training. This is often the case that in DQNs that you should not stack too many hidden layers upon each other, because then it is a really hard job to actually properly tune your weight parameters. Let's also have a look at how this looks for the 256. Yeah, but here you see no big difference. They are really like similar. You could say that the magenta one is still above the other one, but they are both not as good as the one layer or two layer 64-bit for 64 unit layer. Yeah, so that was a comparison of the underlying architecture, and what you see is, or what you should have as a takeaway is, that the size of your neural network is really important for the actual performance of the approximation of the value function of your DQN. Now in the next tests we will evaluate how actually the learning rate influences the result. We will modify the learning rate upon the run, so we will use this guy, and this guy. This one was also from the previous version, so 1 to the power of -3. And we will evaluate these three learning rates, each of them having one hidden layer and 128 neurons. So let's start. Okay, so we did it. We trained 3 runs using different learning rates, 0.0001, 0.001, and 0.1. And for each of them, we took one hidden layer with 128 neurons each. Yeah, so how is the results looking like? So maybe make the other ones away first. Yeah, so that's actually something we already saw. With a learning rate of 0.001 and 128 hidden units, we will actually get some decent results. We will actually reach our target estimation value of 200 in here. But what happens if we take maybe smaller learning rates? This is what happens when you take a small learning rate of 1e minus 5, which actually means that the learning rate is clearly much too small, and the DQN doesn't learn anything. Similar results you will also see if you take learning rates that are too high. So in this example, learning rate of 0.1 is much too high, and your updates to your neural networks and your gradients are too high, and you will eventually always overshoot your target. So what you see is not only network size, but also learning rate requires a careful tuning. In another test, we want to evaluate the influence on the buffer size. So as you heard in the last video, we make use of for the decorrelation of the experience samples, we use an experience replay memory. And at each training iteration, we sample a mini batch, in this case of 32, from this buffer and actually use it for training. The question is, what is the influence on the buffer size on the training circle? For our example, we do the following. We take 32, which is actually one batch size, which basically means we have a correlation between the samples. The next one is we use 5,000 or 50,000 last samples and put them into the buffer. We always use the last ones because we do no prioritization, we do not reuse. So with 32, we actually actually use have a correlation among the targets, and with the other ones not. Let's start it. I will start it and we'll pause the video and we go on as soon as the results are there. And it's done. So it took a few minutes, but we run the 3 different runs. Let's look at the results. So what you see here is this is the results with the original version. We had a 5,000 buffer size, and we managed to actually solve Cartpole very early at this point. What happens if we use a very small buffer size of 32? Actually, the mini batch that we sample is completely the buffer that we actually keep in memory. What you see here is the problem with correlating with correlated data. You see high invariance in the data, and the value function or the gradients always follow the current experienced data, which is very, very small. This is actually a problem, and this is actually what happens if this is close to what happens if you would not use any replay buffer at all. And you get similar behavior when you use a buffer that is too high. So when your buffer size is too large, you have experience in your memory that you always keep on sampling that is very old. So there's experience in your data and in your buffer that is not really necessary for your current experience of your agent. So you just reuse old experiences from before, which in turn leads to the fact that you more unlikely use the freshest experience. So what you see is tuning. So what you see is you see different buffer sizes, and you see that there's also a big variation in those two. And so as a fact, not only the architecture of a neural network and the learning rate are important, but also the buffer size is important. And you can play around with all the other hyperparameters that you can use and tune. And you will see, and I think you will get a feeling that at the end, those methods are still very prone to a proper hyperparameter tuning, which makes them in practice a little limited, or put it another way, you need to do a grid search for every one of your applications. And if you do maybe propose a new method at some point, be aware that those parameters heavily influence the stability of your algorithm and require a grid search over the whole parameter space.